IIT Delhi in 2007 as an assistant professor. At present, he is working as a professor in the same department and also contributing in the progress of the institute, holding various administrative and other responsibilities. He is also a key instrumental in starting the postgraduate program in textile chemical processing. In 2017, it is running over there. His research interest includes functionalization of textiles with metal oxides, smart colorants, use of shear thickening fluids for improving the impact performance of ballistic textiles, coated and laminated structures for inflatables and polymeric nanocomposites. He has very good publications, around 80 papers in referred journals, and also he edited 5 books with this eminent resource person, Professor Butola sir. We are really blessed with your presence over here. Without taking much time, I request Professor Butola sir to start his lecture. Yes, Butola sir, please.
Okay, thank you so much, Dr. Bade. Thank you so much.
Thank you, sir.
Good afternoon. Good afternoon, everybody. Can you hear me?
Sir, already we have taken. Yes, 1 minute. Once again, we'll have the poll afterwards. Once again, the speaker's voice is audible or not, we are checking it. Please vote for it. Be fast. 50% people are voted it. Please go ahead. Remaining, please vote. Be fast. "20 seconds, I am closing it. Be fast. I am closing within 5 seconds. Almost everybody is able to hear you, sir. So we can start your lecture.
Okay, thank you so much.
Yeah.
So thank you, everybody. And good afternoon. My name is Dr. V.S. Butola, and I'll be talking to you today about processing of cotton, polyester, and its blends. So first of all, let me say sorry to you because it's quite late in the afternoon, and I'll be holding you ransom for 1.5 hours, maybe a little less or maybe a little more. And I have been told that there is a mixed background of participants. And there are people from mechanical, there are people from other areas, and there are a few people from textiles also. So I believe that the people from other backgrounds may not have much exposure to textiles. So I have kept the presentation very, very basic. So those who are from textile backgrounds, they may find it a little irrelevant in the sense that it talks about only basic things. But because of the composition of the audience, I had no other choice, but I had to stick to the basics. So basically, I believe that this is about sustainability, and so I'll try to give a glimpse of textile chemical processing, the kind of processes that are carried out, and I would like to draw your attention to the fact that what I am going to talk about involves water at a very large scale in processing of these textile materials, and that way they contribute a lot to the pollution, that is a water pollution. So this has been an issue in the past also, but today we are more aware of it. And when you have a problem, can probably think of solutions. Okay. So I'm not sure whether you can see the slides. Can you see the slides? Is the slide visible?
Yes, sir. It is absolutely visible.
So the next slide, I have changed the slide. So can you see it?
Yes, sir. Textile materials.
Okay, okay. So that means you can see the this thing. So I'll try to start the interaction, and if at any stage anybody feels that need to ask questions, they can interrupt me and ask questions. There is no issue. Okay? So basically, textile. I'll talk about what is a textile material, and I have not taken a technical definition. I have taken a definition from Wikipedia. So basically, a textile material is a flexible material consisting of, you can say, a network of fibers. And when we say fiber, we mean a textile fiber. And what is a textile fiber? It's basically a material which has a shape that is longitudinal. That means uh, the uh, the length is, or you can say L by D ratio is very high. So lateral dimensions are very insignificant as compared to the length direction. Now, any material having that shape will not qualify as a textile material. A textile material has to have certain requirement. For example, it has to be flexible. It has to be heat resistant to some extent. It should be strong enough to withhold the processes of mechanical processes through which it undergoes transformation into yarn or fabrics. And it should be capable of absorbing water. It should be capable of absorbing dyes, and so on and so forth. For example, if I convert a glass into a fiber, I will not call it a textile fiber. So there are certain materials, and mostly these fibers are polymeric materials, which can be natural or which can be synthetic. So we start with a textile fiber, we can convert it into a yarn or into a fabric, and ultimately into a apparel or a garment which we generally wear. Okay. So we start with a fiber which can be produced synthetically or which can be obtained naturally, and then converting it into yarn by spinning, and then that yarn is converted into a fabric. There are different processes of making a fabric. It can be weaving, it can be knitting, and so many other these things. And depending on where you are, so even a fiber is a textile, a yarn is a textile, a fabric is a textile, or even a garment is also a textile. So depending on, for example, in this slide, the first picture shows you different type of fibers. So when they are in a fiber stage, they are very fine, and they need to be converted to other forms. So on the right hand side, you can see yarns which are converted into a yarn after spinning, or you can say twisting the fibers together. And then you can see on this side, there is a fabric which has been converted from yarn to the fabric stage by weaving or knitting. And finally, you convert it into a garment, which we can use directly, okay, or either as a upper body part, upper body garment, or for the lower body part. So these are all textiles. Okay. Now, as you can see, as I just discussed, there are four sequential stages in the before you get a final garment. So first is you need to have a polymer. So polymer synthesis is a separate industry, independent industry, which can create a nylon or a polyester or some other polymer. Now from this polymer you convert a fiber. So there is a specific process which will convert this polymer into a fiber, and it can be again depending on the source. You can get a fiber, for example, from a field, so, or from say a wool from a sheep, or you can create it synthetically, and then you create a yarn by combining these fibers, and finally you can make a fabric, and ultimately you get a garment. So in between, in the red color, I have read wet chemical processing. Now basically, wet chemical processing is an optional process, in the sense that Even without it, you will be able to get a garment. The problem is that wet chemical processing is required. And let's say when we say wet chemical processing, it means that we are treating the textile material in whatever form with a combination of different chemicals and different process conditions, which may mean different kind of pH, different kind of temperatures, different kind of time durations, so as to first remove the impurities. For example, many of the natural fibers will come with a lot of impurities, and in the presence of those impurities, the materials do not have the kind of a feel that we want to have in them. By removing of these impurities, they also make the fabrics absorbent. When I say absorbent, it means that the fiber is able to absorb water. And when we say water, it means that when we are wearing a textile material, shirt for example, so in a humid environment, it should be able to absorb the perspiration generated by the body, so that the person who's wearing it feels comfortable. If you wear a say polythene sheet, which is not permeable to the water vapor generated by the body or the heat generated by the body, you will feel suffocated. So when we wear the fabric, not only it is for aesthetic purpose, but also for comfort purpose. You should feel functionally comfortable. And the most important part, we can say, important part is they impart through this wet processing, we impart a color and design to the fabric. Now imagine a garment that you have, it doesn't have any color or design, so all your garments will be white. Okay, so for some specific purposes that may be suitable, but otherwise we would like our garments to be colorful, and that is done through wet chemical processing. So when we are saying wet chemical processing, we are using chemicals to remove impurities, and we are also using other kind of chemicals which are known as dyes or colorants to impart the color to these. Okay. Now, as I said that even without wet chemical processing, the garment you would be able to create a garment. But if you don't give it a wet chemical processing treatment, what would happen? It will have no color. Okay. It will have a lot of natural and man-made impurities. So for example, I don't know how many of you have seen, if you look at the wool in the raw form, okay, when it is obtained from the sheep by cutting, you will not be able to actually recognize it. It is so impure in the sense that it has almost 50% of the weight of the sheep, the wool, is impurities. And without removing them, it will not be able to, it will be almost very difficult to process them into the form of yarn or fabric, and they will have no appeal whatsoever. Okay? Most of the time, these textile materials in the natural form have a lot of waxy materials over them, so they do not absorb water. Okay? Because of the presence of these impurities, they are relatively stiff. And one very good example is silk. Silk comes with a coating which is known as silk gum. And without removing this gum, silk tends to be quite stiff. Once you remove it, it becomes quite lustrous, shiny, and flexible also. But when this gum is not removed, the fabric doesn't have the luster or shine for which it is known. And of course, they will not be comfortable to wear because of the stiffness, because of the presence of these impurities, because of their non-ability to absorb water. And they will not have any aesthetic appeal. For example, without color or in presence of impurities, they would just be covers and not the kind of garment that we use for aesthetic purposes. Okay. So what kind of fibers? So I wanted to discuss it a little because some of us or most of us know a wool fiber or a cotton fiber or polyester fiber, but it has an importance in the sense that depending on the fiber, its chemistry. So when we say fiber, it basically is at two levels. One is physical level and another is chemical level. So chemically different fibers are different from each other. So when they are different from each other, their chemical treatment has to be different. That means the kind of chemicals employed for purifying them or even for dyeing them have to be different. The conditions have to be different. The pH has to be different. The temperature has to be different. And the first is you can say natural fibers. You can see a picture of cotton on the bottom left side, then wool, and then silk. Okay, so cotton is a different fiber. We know it is a cellulosic fiber. Okay, the cellulose is a building block, and silk and wool are basically you can say protein fibers, which are actually which consist of you can say amino acids. So they are basically proteinous in nature. Okay, so in that sense, wool and silk are not stable in alkaline conditions. So you might have probably noticed whenever we wash silk or woolen garments, we need to use a detergent which doesn't have alkali in it because they are damaged by alkalis. So that is because of the chemical nature. Cotton, on the other hand, can withstand alkalis, but it cannot withstand acids. So while we process them, it is important that we know the chemical nature of these fibers so that we can design appropriate protocols for their treatment, chemical treatment. Then we have man-made. So when we say man-made, man-made means the material is basically natural as far as the origin is concerned, but it is made by a synthetic process. So the process involves some kind of chemical modification, but starting with a natural. So it's just like a paper. You use wood or a tree to convert the wood into a paper. So it is similarly like that. Man-made fibers are those. Natural, you directly get it from the source without any chemical modification. Now then we have synthetic fibers, which we can see as polyester, nylon, and acrylic. Now this polyester it's a material which is sorry, yeah, sorry. So this polyester is nowadays the fiber of you can say the most importance, the highest importance in terms of volume that is being created worldwide. So I think around 45% of all the fibers, textile fibers that are produced worldwide, polyester is at number one. So this remains a very important fiber. And then nylon and acrylic fibers have their specific use, and they contribute towards 8 to 10% each towards the world fiber production. Now I am just trying to show uh, the chemical structures just for the sake of describing their chemical nature. So as you can see, cotton has viscose, cotton has cellulose. You can see a lot of hydroxyl groups there. Then wool and silk, these are amino acids. And then you have polyester, which is synthetic one. So you see a benzene here, and it's basically created, obtained from petroleum products. And then you have nylon, which again is a petroleum byproduct. And again, it has those amide linkages. Acrylic is again synthetic fiber. It's a vinyl polymer. Okay. Now, so there are two stages basically. One is when you have a natural fiber, it comes with its own set of impurities. So you have to remove those impurities before you can actually make a fabric with the comfort and aesthetic appeal. In case of synthetic fibers, that problem is not there. So because they are synthesized in pure form. So there is no need to purify them. Then there is second stage, and that is coloration. So you impart color. So in that case, you have to dye. We call it a process of coloration or dyeing or printing them with colors, so that they can have different kind of colors, which can appeal to different kind of people depending on what kind of uh, choices or requirements these people have. Okay, so for example, there are certain uniforms for police, for army, which have to be specific colors, but for general people, it can be any other color. Okay, so these figures show the kind of impurities that are present in those fibers. So cotton comes out with this varies from the type of fiber to another fiber. 4 to 8%, which is very low actually, quite pure fiber. Silk has 20 to 30. It can have up to 30% of its weight as impurity. So when you purify a silk fiber, the weight can go down by 30%. And silk, as you know, is a very premium fiber, very costly fiber. So in the processing, this is actually taken into consideration. Weight loss, okay? And the price negotiation and price fixing depends on this kind of consideration. In wool, for finer variety, very good variety, this loss can be up to 50%, which is very high. So of course, you can see that when you are dealing with this kind of impurities, this level of impurities, this requires consideration of what kind of chemicals to use, and many times these impurities go into the drain, that is in the effluent. So once you purify the fiber, this will become a pollution which will go into the rivers or our water bodies. Now, this is a slide which we'll see later also. It gives you some general idea about how much water is used for different processes in textiles. So as you can see, this is pre-treatment. Bleaching is purification. Up to 40% of water in a process house, and per kg you may be using 200 liter of water. So to process 1 kg of textile material, we may be consuming, or we may be converting pure water, 200 liters of pure water into impure water, polluted water. And almost 40% of that goes into purification of fiber, in dyeing 16%, in printing 8%, boiler uses 14%, and other processes use a marginal amount of water. So, I mean, while we study these processes, it is very important that we remain aware of the fact that a lot of water is being consumed and being converted into impure water. That it needs to be looked in. So I have just tried to show what kind of processes are used for cotton. So cotton, because as I said, I'll show you some figures later on. But polyester remains #1 fiber as far as the volume is concerned. Then the second number is cotton, and for especially our country, it is a very important fiber because we use a lot of it because this suits our climatic conditions. So singeing is a dry process. Desizing, it is a wet process. A removal of size, which is used for weaving the fabric. Scouring is the removal of the natural impurities, and bleaching is a process of removal of color from the fiber. So if you are going to use this fabric in white form, then you have to bleach it. That means you have to remove the impurities, colored impurities. And then there is another process called mercerization. It is basically alkyl treatment, and this is again optional. And then you can dye it or print it, whatever. The second stage could be the coloration of textile, and this can again be done at various stages. You can dye it at a fiber stage, yarn stage, fabric or garment stage. You can use dyeing or printing for coloration. And these processes, dyeing, I'm talking about dyeing processes, can be batch process. Batch means you have a small amount of fabric and you dye it in one go. And then you have a continuous process in which the fabric is dyed continuously. That means you feed it from one end, and from other end, the dyed material comes out at a given speed, at a fixed speed. For example, 40 meters per second, the fabric will keep coming out. Okay. In between these two extremes, there is a semi-continuous where you process it in two different ways, batch as well as continuous. Okay. Now, this slide shows the way the dyes, different dyes, are being consumed worldwide. So right now you can see that in almost 2020 or 2019, the dye market was something like $33.2 billion US dollars. Okay, and in this bottom slide, you can see, sorry, in this the left hand side, the top one, you can see the market share. So China is number one, and the second is India. So together they make up more than 50% of the consumption of these dyes. And I would like to share here one thing, that when we try to dye a fiber or a fabric or a textile material with a dye, it is a wet process. Wet means the dye has to be dissolved in water, and from there it goes to the fiber. Now it is not like applying a color or coating or painting. Okay. Now the thing is, the dye is absorbed by the fiber, but not all of it. Some of the dye remains in the solution, that has to be thrown away. So if you use a lot of amount of dyes, for example, these two countries, India and China, that means a lot of effluent generation is also taking place in these two countries. And because of that, it remains an area of concern, because if we do not treat this before we release it, it can lead to a lot of pollution happening. Similarly, in this the lower one, you see different kind of dyes. So 62%, the major part is reactive dyes, and then there are other dyes, direct dyes and bad dyes. And other dyes. So we'll talk about these dyes later. So by fiber, this is the global dye share. So for example, cellulose has the highest, 32%, and then second. So even though volume-wise polyester is the highest, it goes into many other applications. So cellulose means cotton and other fibers. So for example, linen, viscose. So in terms of fiber, the largest amount is consumed by this. And this is what is being shown here in this right one, the chemical discharge into textile wastewater. So 50% is salt, and then there are various other chemicals which go into the this thing. And some of them are dyes also, 3% or something like that. So even a very small amount of dye, if it is released into water, is actually can make the entire water colored, which is very, very disturbing sign. If you see a river in a red color or a lake in yellow color, that is not a very good sign. That means a lot of pollution is taking place. So these issues need to be discussed when we talk about sustainability. But my job here is to inform you about what can happen in a textile process industry. And as is mentioned here, something like, it may vary, but something like 200 liters of water is consumed for preparing 1 kg of fabric. And again, the breakup is given here. So this is not come out properly, but anyway. So I'll give you a brief background about what is a color. Okay. So we all have used colors at different stages in our lives. When in school we have painted or created things with different kind of watercolors or oil colors and all those things. We have, many of us may have probably painted our houses or walls with paints. Okay, so in that sense, all colors are similar. Similar in the sense that when you apply it on some substrate, it may be a paper or fabric, that substrate becomes colored. Okay. So as far as that thing is concerned, there is a similarity between different kind of colors, whether you use it for coloring your notebook or dyeing a textile. Okay. So a little bit of physics is there. So what is happening is all our textile materials, say cotton, wool, and others, they are all organic compounds, carbon compounds. Similarly, all our colors are also organic compounds, the one which we use for dyeing of textile materials. Now, there has to be a specific kind of structure if a color has to be a color. Okay. So for example, if you have a compound which is saturated, which doesn't have a double bond, so it absorbs light in a very low wavelength region, that means UV region. So when it absorbs that light, we cannot see it because it is not absorbing in visible. So for any material to be colored, it should absorb in that visible region between 400 to 700 nanometer. Okay, and it absorbs some wavelength, and the remaining, the complementary, we see. Okay, so something doesn't absorb anything, it reflects everything, then we see it as white. Something which absorbs every light, we see it as black, and all other colors come in between. So that means a material is absorbing some radiation and not some others. Okay. Now, when you have a saturated compound, uh, this has a lower absorption. I mean, much below the visible zone. But when it has a unsaturation, then it starts absorbing at a higher wavelength. That means when you have a double bond, its energy of excitation is slightly lower, so it can absorb light of lower energy. That means higher wavelength. Now, when you make a compound which is conjugated means a series of double bonds, alternated with single bonds. So its absorption starts going towards the higher wavelength. That means towards the visible region. So at some stage, if the number of double bonds is enough, it will start becoming colored. So for example, there is an example I'll show you. So this is a compound which is basically diphenyl polyene. So this polyene is basically CH double bond CH, and this is a you can say unsaturation. Now, if you have multiple units of this, okay, so the compound will start absorbing. For example, if you have only one, it doesn't have any color because it is absorbing UV. When you have n equal to 2, it again is not absorbing. When it is n equal to 3, it will start absorbing in say that 400 region when it appears yellow, and then the color starts moving towards the red zone. Okay? So when you have very high number of conjugation, then it will start absorbing a lot of wavelengths and it will start appearing blackish. But otherwise, from pale yellow to greenish yellow, then orange, then brownish orange, and all that colors can be visible. And I have tried to show one specific example here. This is graphite. Now you can see the graphite is a kind of condensed structure, all carbon and all double bonds, so many double bonds that it is absorbing very strongly in visible vision. And because of that, it appears blackish actually. Now, as you can see here, or as I just mentioned, all our dyes, the ones which we use in textiles and also others, they are all organic compounds and aromatic compounds. Why aromatic? Because the benzene ring provides the conjugation. So they will have a different number of benzene rings, and that helps to create a conjugated double bond system. So all our dyes are conjugated double bond systems. That means there are a lot of double bonds alternating with single bonds, and that helps them to absorb light in such a way that we can see them as colored compounds. And then there are other groups attached to them, which are known as chromophores and exochromes. I will not discuss it too much. And the presence of these groups allows the compound to be smaller, because when the compound has too many double bonds, size becomes very large, and then the dyeing becomes difficult. Okay, I'll come to that part later on. So these are some of the chromophores. Chromophores means these are the groups that absorb light. Okay, so having a single chromophore may not give you the color, but it can definitely give you the starting point. So when you have a exo group, for example, this is a chromophore, you attach it to benzene rings, that is aromatic parts. So you have an conjugated system. So this can result in color formation. Similarly, you can see there are chalocyanins, and this is known for its beautiful turquoise blue color. And then anthraquinone. These are all chromophores which help to give you color, but they are just part of the larger group. So there is a dye molecule in which there will be a chromophore. Then these are oxychromes. They help to intensify the color, and because there can be sorry, there is something wrong. Okay, so anyway, I think there is some problem. I'll just like to say that we have a large number of coloring compounds or dyes, and I had shown you a slide in the beginning that the chemistries of these fibers are different. Now it is important for us because I just cannot choose any dye and try to start dyeing a textile. The chemistries of the fibers and the chemistries of the dyes have to match. So that means there are a large number of dyes that are available to us, which we can choose from. Now, how do we choose them? Becomes complicated because there is a very large group. So, for our sake of convenience, what we have done is we have tried to classify these dyes into different groups, and these classification systems can be different. So, I have tried to, although it is not visible in the slide, I have tried to show one classification which is based on application. Application means which dye for which kind of fiber. Okay. So I think that slide will probably come. Okay, yeah. So for example, we have a group of dyes which are known as acid dyes with a specific set of properties which are known for dyeing protein fibers. For example, it can dye wool, silk, nylon, and other fibers. Then there are another kind of dyes, basic dyes. And acid means this requires acidic medium for application. Basic means it has cationic nature. It is used for acrylic fibers. Then there are direct dyes, which are again anionic, and these are used for dyeing cotton and other cellulose fibers like linen or viscose. Then there are white dyes, which are basically without any charge and which have to be converted chemically into a form uh, which can be applied on a cellulose fibers. In fact, one of the very important and very famous dyes known as indigo. You might have all heard about indigo, which is used for dyeing of denims. And denims is a kind of classic material which has been in use for a very long time. So that indigo is comes into the white dye class. And then reactive dyes, which is again used for cellulosic and the fibers. Then viscose dyes for dyeing polyester and other fibers. Okay. So now when I show this slide to you, what I'm trying to convey to you is that depending on that earlier slide where I had tried to show the chemical nature of these fibers, the nature of the dye has to be such that that it is able to form some kind of chemical bond or some kind of chemical interaction with the fiber. Otherwise, it will not be applicable on the fiber. For example, if you take a direct dye, which is ionic dye, and if you take a polyester, which is a hydrophobic fiber, it's like an oil. And if you try to dye polyester with a direct dye, you will not be able to do it because polyester being hydrophobic, oily in nature, direct dye being anionic or you can say salt-like, water-loving, they are not compatible with each other. So while you select the dye, you have to be aware of the chemical nature of the fiber as well as the chemical nature of the dye also. Now, these dyes some issue. Anyway, so the dyes, what are the dyes? This shows the definition of the dyes. These are color compounds. That means they absorb in 400 to 700 nanometer electromagnetic radiation range. They should be soluble in water because we are applying them from solution, water solution. If not, they should be converted into a condition in a stage where they are solubilized. So, for example, indigo is not soluble in water. So we have to convert chemically it into a form where it becomes soluble, and then later we convert it back into its non-soluble form. Now the third point is purchase affinity for the substrate. It has been almost 45 minutes. I would just like to know whether I'm audible, whether people are able to follow what I'm saying, whether it's too technical or whatever. Any feedback? Hello.
Sir,
Am
you
I
are
audible?
perfectly audible. The participants are also appreciating your lecture. There's a
Okay.
remark in the question box also related to you.
Okay.
Once again, I request participants, if you have any question, any doubt, or any suggestion, please write in a question box. But lecture is fine, sir, and you are going very good way.
Okay. Okay. So fine. Thank you. Thank you.
Yeah.
Because it's late in the afternoon and they may be tired also. Okay. Anyway, so the point number three, I would like to emphasize purchase affinity for the substrate. So, for example, the way we have been doing drawing or painting in our school in a notebook, or the way we paint our walls is totally different from the way we dye our textile materials. Okay, so when we make a painting on a notebook or on a wall, we are simply depositing the color over the substrate. Okay, the textile dyeing is totally different. In the textile dyeing, what we are trying to do is we are trying to uh, use the coloring compound in its molecular form. That means it has to be completely soluble, and then it has to diffuse inside the fiber. Okay, and it should not be, we are not depositing it. So it goes inside the fiber. So when you wash the fiber or the textile material, it should not come out. When you put it in the sunlight, it should not fade. That means in the process of dyeing, we are making the dye and the substrate one. It becomes a part of the fiber. It does not affect any of the physical properties of the fiber. It doesn't change the strength. It doesn't change the dimension, or for that matter, any other property. Okay. So what is happening is the color in its monomolecular form has gone inside the fiber, and when it goes inside the fiber, it should remain there, and that will be possible only if it is able to make some kind of a strong interaction. It can be van der Waals force, it can be hydrogen bond, or it can be a chemical reaction also. Okay, because your garment has to undergo washing, drying, ironing, everything. Acha, the other thing is one very important thing for us is that when we apply, so you might have seen a lot of flowers. So in the when the season comes, spring season comes, we see a lot of flowers around us, and some of the flowers are beautiful petals colored like say red, yellow. Okay, and after some time you will see that the flower fades, the color goes. Okay, but it should not happen with our textile materials. That means if I dye a textile material with a dye, it should remain there, whether I wash it, whether I iron it, whether I go into the sun, and it should probably last the lifetime of a garment. So if my garment is serviceable for 1 year, the dye should be there for 1 year without fading. Okay. Now that puts a lot of pressure or demands on the color. So our textile dyes are different in that sense. Okay. And we select them depending on what fiber and what kind of fastness or durability we are asking for. So there are for example, applications where the requirements are extremely stringent. For example, uh, people who are making very high-end cars, for example, Audi or BMW or other cars, they also use a lot of textile materials inside the car, in say car seats or other things. And there the requirement is extremely high. So that means the color should not fade at all, okay? Because it's a premium product. Now, again, this is not visible properly, but anyway, this is for pigment. So pigments are those colors which are just colors, but they are not insoluble in water, and they have no affinity for the substrate. That means if I throw it on a textile material, it will not stick there. Okay? So it has to be deposited. It's just like a paint that I put on a wall or a wood, okay? Or the way I draw, make a drawing or painting on a paper. I'm just depositing it over the fabric, because my wall or my table or my notebook is not going to be washed. It's not going to be put in the sun. So I'm not worried about its durability. So these are pigments. So when we have a pigment, I can apply it on any substrate. I can apply it on a wall, on a paper, on a fabric also, but it will not be washable. Okay, it doesn't interact with the water, and I don't have to worry about selection. Any color on any substrate will do. The another important thing is, when I apply it on the textile material, it has to be applied in a very careful manner so that it is totally uniform. So, for example, when you are say dyeing 5,000 meter of fabric, okay, in one go in a machine. So the entire part of the fabric from one end to the other has to be completely uniform. Again, that puts a lot of pressure on the or the demands on the process and the color also. And it should of course be stable to say washing, light rubbing. And I would like to mention is that nowadays our washing powders or the detergents are very powerful. They have a lot of alkali. They have bleaching agents in them. They have enzymes in them, and they all contribute towards the fading of the color. So what has happened over the years? Because of these stringent requirements, the dyes that are being developed have also become very sturdy. So it's very difficult to remove or destroy a dye, a modern dye, and that's why this problem of a fluid discharge has become very acute. Because if you have discharged a dye in water and it goes to water body, it will not become it will not degrade by itself, because it has been made so strong. In comparison to it, a natural dye, because the nature has made it, nature did not want it to last long, it has made it biodegradable. So when you see a petal, when it blooms, it is very brightly colored. After some time, you'll see it will just fade, it will just vanish. Okay, so when I dye a fiber, this is a fiber, a very fine fiber. The diameter may be only say 20 micron. So when I look at the cross section, it should look like this. So when I dye a fiber or a textile material, the color should be able to diffuse to the core in a very uniform way. Okay. On the other hand, on the right hand side, you see I have just deposited on top of a fiber the color. So I don't want, my dyeing should not be like the right hand side. But when I paint say a pipe, when I paint a pipe, that is how you will see it. Okay? Or when I paint say a cylinder, that is how it will look, a cross section of the cylinder. But in my case, if I am dyeing it, it should look like this. It should go to the core, and that's why it takes time. Allowing the dye molecule to penetrate into the core of the fiber will require certain conditions, and it will also require some time. But when we are just painting or coating it, you just do it quickly. Now in this slide, I have tried to show some of the structures. These are naturally occurring structures, and of course these dyes, many of them are not very stable dyes, in the sense that they may fade in the sunlight. Can somebody identify dye in A? So it is that indigo dye, indigo, which was it is used in large quantities to dye denims, and actually this is not a very new dye. This has been known for centuries, and people have used this indigo dye. It is obtained from a plant which has been grown in India also, and nowadays, because it is being synthesized at a cheaper rate in large quantities, so natural dye production has come to a very small, it has become a cottage industry. But This is, I mean, so these are some of the dyes which can be used naturally. So the question is, why don't we use natural dyes? Because they are biodegradable, they are available from plant sources. Our synthetic dyes are dependent on petroleum. And once petroleum sources go, they will not be able to create them. So the answer is that although they have a lot of advantages with natural dyes, they are renewable, they have no environmental impact. The shades that you create with them, they are quite soothing. They are also safe. The problem is that they're very costly. Costly in the sense that you need a very large amount of dye to dye a textile material in the same shade that you want to get from the synthetic dye. So as I said, over the years, synthetic dyes are being synthesized in a way that they have become very sturdy. At the same time, there is one more important aspect that is called tinctorial value. Tinctorial value means that per gram of the dye, how dark shade can you get? So today's modern synthetic dyes are very high tinctorial value. That means to get certain depth of shade, you require very small amount of the dye. So that gives you a cost advantage. And because they are natural natural origin, and the nature has made them like that, so they are not very stable. In sunlight or in washing, they will fade very quickly. Also, because they are being obtained from natural sources, there's a consistent variation in their quality. Availability varies depending on season, the availability of land, and all those. And the problem is because their fastness or their stability on fabrics are not very good. We sometimes treat them with certain chemicals to make them more stable, which are again harmful. Okay. And sustainability is an issue which is often talked about. But when we look at this, we have to be aware of the fact that just being natural may not be sustainable. For example, I will give you an example. Cotton is a natural fiber. Okay, it is grown in as a crop in a field, and it is then obtained from that plant. Now, people argue that cotton is more green or more eco-friendly because it is grown naturally, and it is better than synthetic fibers. Now, the argument against that is when we grow cotton, we use a lot of water also. But the more important thing is cotton is very pest-prone crop. That means it is attacked by a lot of pests. So cotton farming requires use of a lot of pesticides, and that itself makes it a non-green or non-eco-friendly fiber. Okay. So while considering whether it's sustainable or eco-friendly, we have to look at the entire life cycle of the material. So now, just giving you a background, the morphine is a dye which was synthesized first, I think 1856, almost 150 years ago. And you can see this is a very bright color. These such bright colors on the left hand side, such bright colors are not obtained using natural dyes. And his son has displayed this. They dyed silk with this dye, and you can see the kind of attractive shade that they were able to obtain. And this was also the first dye that was mass produced. Okay, and indigo is also again a natural dye, but nowadays it is being synthesized. So you can say at some stage after the morphine was synthesized, this indigo was also made in a synthetic process, through a synthetic process. And one of the persons who actually developed this process went on to win Nobel Prize in chemistry in 1905. Okay. So this is the starting material here, and this is the product. You can see this has a connection with India in the sense that Mahatma Gandhi started his first satyagraha movement in India from Champaran, Bihar. And what was happening was the British at that time, because in 1970 British were there, they were forcing the farmers of this Champaran to grow indigo. So that is indigo plantations. They were obtaining indigo from the plants without paying them much. So they actually protested, and Gandhiji led this protest, and after that he became the the history after that. Okay? So I brought this slide because I wanted to give you a perspective. When we say natural dyes and when we say synthetic dyes, modern synthetic dyes have consistently over the period have evolved. They have very high tinctorial value in the sense that very small amount of color will give you a very large amount of colored fibers. Okay, so you have to spend less amount and less money to get the same depth. They can give you very bright colors which are otherwise not possible with natural colors. They are very stable because they are made like that in sunlight, humidity, washing, ironing, or even say dry cleaning and all that. And they are cost effective because they are being mass produced, and mass production brings down the cost. Variability is less because they are synthesized in pure form, so consistent quality is there, and they are easily available in large quantities. So what I'll do is I'll try to probably cover a few dyes, maybe one, maybe two, maybe three, to give what is happening actually. So first dye that I have tried to cover here is the direct dye. So this direct dye is basically called direct dye because its method of application is very simple. It is basically a direct method. So we call it a direct dye. So what you do is, if you have a direct dye, you just put it in a vessel and put some water, dissolve it in water, and put your fabric in it, heat it for some time, and the fabric will be colored. So it is as simple as that. There are some processes which are very complicated. So that's why in comparison this is called direct dye. Now, there are some features in the sense that before going to that, maybe we can have some look at the structures. So this will give you some idea about. So these are not very good dyes in the sense that their fastness, washing stability is not very good. In Punjab, a lot of people, if somebody is here, Sikh people, they use this direct dye to dye their pagris. Okay? So they can be colorful, they can be brightly colored, but whenever you wash them, the color comes out gradually. So the turban will fade. Okay? So you do not use it for areas where the color bleeding is a problem. Hello? Yes?
Sir, continue, sir. Sir, continue,
okay.
Sir.
Okay, fine. So, as you can see, the areas which requires less washing, say curtains or carpets and ribbons, or where the value is not very high, it is used there. 75% direct dyes are azo dyes, and I would like to show you the structure which can give you some idea about. So, for example, in this slide, so at the bottom, this is sorry, it's not coming out properly. So this dye at the bottom, you can see this is a planar or linear structure. Linear means it is kind of elongated. You can see there are 6 benzene rings here. Okay, they are joined by 2 N double bond. This is called azo group. So there are 2 chromophores. This helps in continuing the conjugation. So conjugation means 1 single bond, 1 double bond. So you can see there is a very large conjugation here. The coloring component, the dye is very long, and it is able to form a hydrogen bonds with the cellulose. Okay, so this is the affinity of the fiber and the dye, between the dye and the fiber. Now the problem is these hydrogen bonds are not very strong. Water is able to break them. So you can apply it on a textile material, but when you wash it, the water is able to break these bonds, and the dye starts coming out. Okay, and you can also see at the bottom there is SO3 minus group. So this SO3 group is basically it's a solubilizing group. This is an ionic group, and because of this, the dye is soluble in water. If you remove this group, this dye will not be soluble in water, and then you will not be able to apply it on the fabric. So the structure is, it is made like this deliberately. It has a linear long structure which is able to bond with the fiber with relatively mild forces, not very strong, not very weak, but milder you can say. So it has some, if you use it for dyeing, say curtain or a ribbon, it will remain there for some time. If you start washing it, it will gradually start coming up. So this is not an ideal situation, but anyway, this is what we have. Now this is another dye. The same dye, sorry, the same dye, but what has happened is you can see there is a uh, copper now. So this has been made copper complex dye. So because of the copper, this compound becomes stable and it doesn't fade in light. Okay? So the color changes slightly. So it becomes a different version of blue. So this is a technique that is generally employed for improving the fastness or stability of the dyes. And then this is another dye. I'm not sure why this is happening. So this dye is a green dye basically. So what is happening is in this dye basically there are two different chromophores. Hello. So I had shown one slide where this is a chromophore. This is a anthraquinone, and this is another. This is azo. So these actually this part of the dye has one color. This is blue or yellow. I don't remember, and this has a complementary color, blue or yellow. So when you combine both the chromophores in one dye, it has a single color, that is green color. Now this kind of color preparation, where you have two different chromophores in the same dye, it gives you a brighter color. The other possibility is you take a different kind of separate dye which is yellow and separate dye which is blue and combine them. That doesn't give you the same kind of this brightness. Okay. So what I was trying to highlight here is these direct dyes have to be very large in structure. They have to be very long. Otherwise, their affinity or their bonding with the fiber will be too weak. They will not be able to withstand any washing. So there are some other dyes. I hope you can see the structures. Again, what I am trying to highlight is that they remain somewhat linear and longer structures. Okay. This one is an exception. This is a specifically made, you can say, it's known as copper thiocyanine, and this is the only chromophore that is able to give a very bright turquoise blue color. Again, the problem, because we can see structure, it's very difficult to apply the fiber, and it doesn't give you washing process. It keeps it keeps bleeding when you wash it. Now I'll skip this. I'll skip this also. I'll try to come to the reactive dye. That is the biggest market we have seen this. So this is important in the sense that when people found out that direct dyes have poor fastness issues, and there are certain applications where this cannot be acceptable. For example, in case of military or school dresses or dress uniforms for certain applications. So what people did was, because the root cause was poor bond, so a different class of dyes was developed, and this is called reactive dyes because this dye is able to react with the fiber. When I say react, it actually means is it forms a covalent bond. Now covalent bonds are much stronger than hydrogen bonds, so the dye does not bleed at all, and this has given a lot of preference to these dyes. So they have now, we can say, very large market for cotton. Now again, in addition to what we had in direct dyes, you have a reactive group. Everything else is there. Chromophore is there, solubilizing group is there. Then you have a reactive group, and the bridging group is what bridges the reactive group with the dye. Now I would like to show it here. So in this dye, this is the reactive group, chlorotriazine. Okay. So the chlorine here and the chlorine here is the reactive group, and this is the dye molecule. This one, and so this is the dye molecule here. This NH is the bridge, and this is the reactive group. So what we have done is you can take any dye and react it with the fiber. Sorry, with the dye molecule. Now this part can react with the fiber, and because this is reacted, it forms a covalent bond. So the entire dye molecule also remains connected, and it doesn't get washed out. So these dyes have very good fastness properties on a cotton fabric or any other cellulosic fabric, and that's why they have become popular and more in demand. Okay, so this dye name is Ci reactive red 1, and you can see there are 2 chlorine atoms. So this is dichlorotriazine dye, and then there are some other groups. Okay, so these are different groups, and these are the brand names of the dyes which are used. So there is, you can see a lot of reactive dyes are available in the market, and you can choose them depending on your requirements. And these are monofunctional. That means there is only one group which can react. Now what happens when you have one group? So part of this group is not able to react with the fiber, so some of the dye is wasted. So what people have done is they have now attached 2 reactive groups. So when you have 2 reactive groups, the probability of either group or both group reacting with the fiber increases. So the dye utilization improves. So for example, these are monofunctional groups. So for example, in this case, this is the reactive group. In this case, these 2 are reactive groups. In this case, this is the reactive one molecule that will react with the fiber. And on the other hand, you have this dye, bifunctional dye. So either this can react, or this can react, or both can react. So this becomes bifunctional dye. Then these are monofunctional dyes. I think I'll skip them. And there are various other systems also. Just skip them. That is probably not needed. So you can see here. So what I wanted to emphasize here, if you compare it with the direct dye, so the structure is very small. So in case of direct dye, we needed a very large structure because we needed multiple hydrogen bonds between the dye and the fiber, but because the dye did not form very strong bonds, so we needed multiple weak bonds. In this case, I need only one bond, a reactive bond at this place. So my dye molecule doesn't have to be very big. A small dye molecule will help. In some cases, you will find there are certain dye molecules which are much larger. So there is another purpose. I'll not talk about. So for example, this reactive dye also a very large structure, but then it is a very totally different purpose. So anyway, so I'll just skip this also. And this is the way we apply it. So what we do is we start heating the dye bath at 40 degree. We go to something like 70 or 80 degrees centigrade. And in between, in the beginning, we add the dye in the bath, and we also add some salt, which can be sodium chloride. And sodium chloride is actually something which helps the dye transfer from the water solution to the fabric. Otherwise, the pickup the dye from the solution is not very good. And this soda ash, this is an alkaline. This is used for reaction of the dye between the dye and the fiber. So without this soda ash, the reaction will not take place. So now, as you can see, this system is slightly more complicated than direct dye. In the direct dye case, you put the dye, salt, and the fabric together, and this is done. Here, what you have to do is, once the dye has been absorbed, you have to add soda ash, which is an alkali, and then only the dye is complete. Okay, and after that, you have to wash it also. For these certain dyes, will get hydrolyzed, which has to be removed, and these are also quite lengthy process. So this is a lengthy process basically. So this is a general sequence which I have just seen in the previous graph, and these are other various approaches. So the reactive dyes can be applied to a lot of processes. The The most important thing is how to bring about the reaction with the fiber in the dye. And this can be done in many ways. It can be done by just keeping it at room temperature, or by heating it, or by steaming it, by providing energy and all that. Just many system. I will not like to discuss them here. And then one important thing is some of the dye which is hydrolyzed, which does not have, which has not reacted with the fiber, has to be removed, and that can create problem, because that will give you an impression when you wash it, it will start coming out. So this has to be removed, and that is done at very high temperature for boiling, of course, almost boiling the fabric for a long time, for a few hours. So that increases the input cost of the reactive dye. Okay. Now I would like to take another fiber, which is polyester, because these two are the main two fibers, and they are contrasting in the sense that cotton is cellulosic, it absorbs a lot of moisture. Polyester is synthetic, it does not absorb moisture at all. Polyester is like oil or fat, so you need to use a different kind of dye for this. Cotton is natural water loving fiber, so you need to have a dye which is water soluble. Okay. Now you can say these are different stages. This is a polymeric material, grains. This is a fiber. This is a yarn, and I think this is not important. I can just skip it. I would come to this slide. This shows global production of fibers. Although the data is slightly old, of 2010, you can see the cotton percentage world share has decreased from 1980, when it was almost 50%, to 40%, then 31%. I think it is less than 30% now. Wool has remained almost constant, 5.4 to 2%. Viscose has gone down. Polyester from 18.5% has become 40%. Today it is even more. I think it may be 45 or 50%. So this is a major fiber, and then cotton is a major fiber. All other fibers you can say. Polypropylene is not actually a textile fiber. There are other minor fibers. So let us see. So when we are dyeing polyester, we need a different kind of dye, and we call it a disperse dye. So a disperse dye is a relatively, you can say, hydrophobic dye, that is slightly polar but non-ionic. So it doesn't dissolve in water. So what do? You do not dissolve, because it doesn't dissolve. We disperse it in water. So we use a dispersing agent. So the dye is present in water, but not in a solution form, but in a dispersed form. And you can see again a large number of benzene rings there on the left hand side top corner. So this is again a small molecule. So what is happening is because polyester does not absorb water, the dye is not soluble in water, you somehow push the dye inside the fiber. So once the dye goes inside the fiber, there is no chance that it can come out, because the water will not go and it cannot come out. So it is mechanically trapped. So I don't have to make a very large structure which will have some kind of strong bonds. I just need to push it inside the fiber, and then I'm free, because it will not come out. And these dyes typically have low molecular weight, and they have another tendency, because they are non-ionic. They have this property of sublimation. That means if you heat it, it doesn't melt; it simply gets converted to vapor form. Okay? And when you are putting it in water, they will remain in the form of a particle of size 0.5 to 2 micron. And so when you have to apply it, you just make a dispersion. And these are some of the structures here. You can see they are smaller than direct dyes, and they have typically only one azo group. In case of direct dyes, we had seen two azo groups. So there are two benzene rings typically, okay? And there is no solubilizing group. Some of them are slightly polar, but there is no solubilizing group. So they are not soluble in water actually. These are some other structures, and I wanted to highlight this fact that The solubility of these dyes in water, milligram per liter, that is almost ppm. For the structure which I had shown, which we have seen in the previous slide, is very low. That is almost insoluble. But when you heat them, this solubility increases significantly. For example, for dye 7, from 7 to 240. So during heating, the dyes become slightly more soluble, and only the soluble dye will actually be absorbed by the fiber. Okay? So this is an important concept. And what is happening here is, in this part, what is being shown is that the bigger particles start breaking into smaller particles. The smaller particles start dissolving in water, and the dissolved dye starts getting absorbed. So as the dissolved dye get absorbed, the particles keep breaking, and this, this equilibrium keeps shifting towards the fiber. And when the fiber is saturated, the process reaches an equilibrium, and you have to stop there. In fact, you have to stop much earlier, because this dyeing process can take a long time. So what is happening is, basically I have just described, the dye gets dissolved and then gets absorbed by the fiber, and this process happens at a very high temperature. You have to go to up to 130 degree for this. So because water boils at 100 degrees centigrade, so you have to use a pressurized vessel to do this dyeing process. And what is happening here is, the dye is distributed between the fiber and the solution, that is water, in a ratio which is constant. Okay, so in this graph, this df is the dye in the fiber, ds is the dye in the solution, and this straight line, this is called Nernst isotherm. So this is applicable for polyester fiber. That means whatever amount of dye you take in the solution, the amount in the fiber and the amount in the solution will remain constant. Okay? That means as you increase the concentration of the dye in the bath, the concentration of spent bath, that means the dye that is left in the bath, will also increase. So the entire amount of the dye will never be transferred to the fiber. There is always a partition between the fiber and the water. That is what makes it complicated. So there are various methods of dyeing this. There are basically two ways. Carrier dyeing is not, of course, not practiced nowadays. So there is HKSP dyeing, which is carried out at 130 degree. And this vessel here, you can see this is a typical machine, which is pressurized. This is closed from all the sides, so you can generate a temperature of 130 degree inside, and the fiber gets dyed. At 100 degrees centigrade, it is difficult to dye. And then there is another method which is called continuous dyeing method. And in this process, actually you go to a temperature which may be up to, say, 200 degrees centigrade. So there, because this is a thermodynamic process, and these processes are actually, the rate increases with the temperature increase. So at 200 degrees centigrade, the dyeing is so fast that within 30 to 60 seconds, the dyeing can be over. At 130 degrees centigrade, it can take up to, say, 90 minutes or 2 hours. So in exhaust dyeing, basically, this is what is happening. You start at 60 degrees centigrade, the dye in the dispersion form, and you increase the temperature to 130 degrees centigrade. By this time, most of the dye is solubilized in water. And in this 45 to 50 minutes, the fiber will absorb most of the dye. And when it has absorbed most of the dye, you stop, you reduce the temperature, and then you discharge the effluent. Okay? So this is how it works. Carrier dyeing we are not taking. Then we are talking about high this thermosol dyeing. So what is done here is, the fabric is saturated with the dye, which is dye dispersion basically, and at 180 to 220 degrees centigrade, you heat it for 30 to 60 seconds. Now I had just described that in a previous slide, that these dyes undergo sublimation. So at around above 150, they will start sublimating, and because the dye is actually in contact with the fiber, after sublimation, the vapor of the dye diffuses into the fiber, and because the temperature is very high, the process becomes very fast. and within say less than 1 minute, the fiber or the fabric can be dyed. Okay. Now this process cannot be repeated for say cotton, because cotton first will degrade at around 200 degrees centigrade. Secondly, the dye for cotton will not sublime because they are ionic dyes. Their evaporation temperature is very high. So there are various advantages of these this process, because this is a very fast process, and in this process, because you do not have a solution, the dye is actually over the fiber, so the dye utilization is very good, and energy consumption overall is lower because the process is much faster. Actually, what happens when you heat water and we reach a temperature of 130, the amount of heat required is actually much higher than raising the temperature of a dry fabric to 200. So that way, the dye utilization as well as but the problem is the process is very fast. The speed may be 60 meters per minute. So this can be utilized only when you have very long lots of fabrics to dye. So for example, if you want to dye say 20, 30, 40,000 meters of the fabric in one go, then only you use this process. This is not feasible, commercially feasible for a small lot, say 5,000 meters. Because the process speed per hour is almost 3,000 to 4,000 meters. And setting up the process for this takes a lot of inputs. And after that, what happens actually is the dye, some of the dye remains on the fabric surface, which needs to be removed. So we remove it by reduction, and we call the process reduction phase. Because I was not sure about the background of the candidates, and I didn't know about how much they would appreciate what I am discussing here. So I have not gone towards the blending, but I would mention that part in a few sentences. Say a lot of times we have to dye a blend of polyester and cotton. Okay. Now the same principles apply for dyeing cotton. You have to do the dyeing with a dye which is say reactive or direct dye, and for dyeing of polyester you have to use a disperse dye, and you have to apply the same conditions also. That means for polyester you have to go to 130 degrees centigrade. For cotton you can do dyeing at 70, 80 degrees. Now there is an issue in the sense that for example, dyeing of cotton with reactive dye requires an alkaline medium. For dyeing of polyester you require an acidic medium. Now these two reaction conditions are actually dyeing conditions are not compatible. So what do you do? So what we do is generally the practice that is practiced is that we first dye polyester. So we have a blend in which both the fibers are mixed intimately. So when we put the fabric, a polyester cotton blend in the dye bath which contains only disperse dye, only the polyester part gets dyed. Okay. After that, what we do is we drain the liquor. That means it has everything. We wash the fabric and we refill the dye vessel or the dyeing machine. This time we put the dye which is meant for cotton part, and this time we when we dye only the cotton part will be dyed. Okay. Now the thing is because the dye for cotton will not be absorbed by the polyester, and the dye for the polyester will not be absorbed by the cotton. So we don't worry when we dye them separately, individually. The probability of contamination or mixing of the dye will not happen. So for example, if you dye cotton with the red dye, so the cotton will be red, and if you dye polyester with say blue dye, the polyester will be blue. And the mixing will not take place because these dyes will go on a different fiber. Okay. All other considerations remain same. The only thing is now in place of one go, you have to dye it in two stages. At one stage, you dye polyester. In the second stage, you dye cotton. And generally, the cotton part is dyed later. Polyester part is dyed first. Because some of the dye, disperse dye can, you can say, stain cotton part. So once we dye the cotton, the uh, polyester part gets dyed, cotton gets stained. So we remove the staining from the cotton part and then we dye the cotton part with reactive dye or direct dye. I think the time is also up. It is quite late now, 7:30, and I'll stop here. Uh, I'm open for questions. If you have to ask any questions, you can proceed with them. I'll be very happy to answer.
Sir, thank you very much for your wonderful talk. And your time flexibility also. The lecture is you have kindly permitted us to keep the lecture at 6 o'clock. Most of the participants are still with us, and this is that very nice informative lectures from Siddharth Patel. There are very good comments coming out of one of the participants is saying that spray dyeing technology. Hello.
Can you repeat, please?
Spray dyeing technology is how much successful? Is it viable commercially? Spray dyeing.
See, the thing is, today the problem is the customer, because you are not dyeing small lots. See, the dyeing is viable only when your lot size is at least 500 meters, okay, or larger. Now, if you are dyeing with the spray dyeing technology, for small lots, very small lots, say 10 meter, 20 meter, you may be able to get uniformity, but very large lots, it may be difficult, because when you dye a lot which is say 10,000 meter long, using spray dyeing to get the uniformity at each stage or each part of the fabric may be difficult. So it may be successful if the customer is not very he doesn't care about the variation a bit. But for somebody who is very much into the requiring totally uniform
quality.
Yeah, so color uniformity. So then it may be an issue.
Okay, hopefully Naresh, you got this answer for your question.
So I'll give you another example, because when you dye fabrics or garments using natural colors, so there is always a variability in the color because of the source. But the people who use these kind of garments, they do not insist on exact shade matching. So they will accept the variability. So there it is not a problem. Similarly, if a customer is ready to accept that, I think that will not be a problem. But if they insist on having that kind of uniformity, then it may be an issue.
Hello, sir. Are you audible?
Yeah.
Yeah, sir. Can you show your camera? Can you switch on the camera so that audience can able to view you, see you?
Camera.
Yeah. Your webcam is there. In webcam, you just click on that and you just say that share my webcam. Yeah.
Yeah. Yes.
Yeah. Very good, sir. Yeah, Maiti sir. If you are there and you are able to listen to us, can you come? Yeah. Parikh sir is also there. Mr. Parikh is from Mantra sir, and he's having a good experience of 40 years as a senior researcher over there. And Maiti sir, already you know that as a student in IIT Delhi.
Yes.
Sir, can you give your concluding remark? Dr. Maiti. Parikh sir, if you wanted to say something, you can say after
yes.
Maiti sir. Yeah.
Yes. Thank you, sir, for giving a so nice lecture and covering almost everything, starting from fiber type, chemical nature of fiber, dyes, type of dyes, and chemical nature of dyes, and how dye fiber react with each other, and what are the dyes which will not react with which type of fiber, and when the dyes have no actually reacting groups, how it is attached with the fiber. So many things has been covered, and what are the properties of the dye should be there, what is the main thing like tintorial value, fastness property, and all these things. Then what are the property of modern synthesized dyes, followed by a dyeing process for particularly cotton and polyester and its blend. So I think everything has been covered so nicely. We should not. I think I need not to say anything. So thank you once again, sir.
My only fear is that because this was so different for other people, people from non-textile background.
Yes, sir. So
they have not been able to understand anything out of it.
So we are doing like this way for say fiber spinning, yarn spinning, and weaving process also, and this is dyeing process. So it's a compact things. What we are trying to give some idea about the textile process.
So this is going to be definitely a value addition to them. And being participants from different backgrounds, they may get what is happening actually in the textile, which is very close to the human being. It is considered to be the need, one of the fundamental need of the human, but we know very less about how we are getting the garments and what are the process on that. We are happy to see the various colors, but in the basic physics of the color is, I think we don't know. Still, I was not aware of this many processes need to be carried out, and these are varieties over there. Okay, handing over to the Mr. Parikh sir.
Yeah, it was a very nice talk, and looking at the type of the participant, because majority are from non-textile background. Butola sir, you have done a very nice job in giving them basic idea about the dye and the fiber and how it connects. And so this is definitely it will make a very good base, because tomorrow I and Dr. Maiti will be talking about sustainability and machine parts of the processing, textile processing. So you have made a very good background for that. So thank you very much for that.
Thank you. The only problem is that what I try to cover here, I take generally 60 lectures to cover that. So this is 60 lectures condensation in 1.5 hours.
Yeah. So it's a very vast. I mean.
So for me, it was very difficult to think what should I include, what I should not include, because the topic was very general, not specific.
Yes, sir. Definitely, it is a Herculean task for you to convert 16 hours within 1.5 hours, and that is also the participant which are not in the textile background. But our participant Sanchita says that very informative, nice session. Prashant Ray is also saying it's a very informative session, sir. Thank you very much. So participants are happy to listen to your lecture. Now it is already 7:40 and I think everybody is waiting for the dinner. So
Exactly.
without taking much time, I think we can close the session. If Dr.
Sure.
Kalyankar is there and wanted to say something, please. Dr. Kalyankar.
No, sir, it is perfectly okay. The participants are really getting benefited by this good knowledge shared by all these reputed speakers. And hopefully in all the remaining 3 days, they will be highly benefited by the remaining sessions. Okay. So thank you, Butola, sir, for spending valuable time.
Thank you so much. Thank you so much. Thank you.
Participants,
Thank you, Parikh, sir.
request
Thank
is
you,
there.
Maitri, sir.
Yeah.
Thank you.
There is a special request
Thank
for
you.
the participant. Tomorrow we are going to start the session at what time? Is anybody remembering? 9 o'clock.
9 o'clock.
Tomorrow's session is going to be starting at 9 o'clock, 9 to 10:30, 11 to 12:30. Normal sessions are going to be there. Actually, sir, today we have started the lecture at 2 p.m. So morning session there was no lectures, and we have kept all the lectures in afternoon session. But tomorrow we are going to start 9 o'clock. So be ready at 8:50 to join this SCT FDP. Okay. So with this, I think we'll once again thanks to take out the valuable time for this lecture and preparation. Thank you, sir, for this wonderful and informative talk once again. Thank you, sir.
Thank you. Thank you so much and good night. Good night to everybody.
Good night.
Good night.
Good night.
Okay. Have a great
Yeah, bye.
night.
Bye.
Bye. Bye. Bye. Everybody.
Ah. Okay, sir. Maiti, sir.
Yes, sir.
We can take a leave, so you have to come early tomorrow. So we don't want to take your
Yes, sir.
much
Yes,
time.
sir. No, sir. No, sir. Okay. Okay, sir. Okay, sir.
Yeah. Okay, sir. Bye. Huh?
Okay, sir. I am going to end the meeting.
Yeah. Yes, sir. Sure.